the Associate Director of the Institute. And I think everybody knows who we are. We're a collaborative research institute in theoretical computer science. And this semester, the two programs that we're running entirely online are probability, geometry, and computation in high dimensions, and the theory of reinforcement learning. And together they've involved around 200 participants, an unusually big number for a very unusual semester. So welcome to the final workshop for the High Dimensions program, final workshop for the semester, which is on learning and testing in high dimensions. A big thank you to our events coordinator, Jesse Gill, for all his work on the logistics for this workshop. Thanks, Jesse, and to Omid Farr, who's our videographer. And a big thank you to the organisers, to Adam Clivens, Guy Bresler, Sebastian Bubeck, Ninja Day, and Philippe Rigolet. They've done a fantastic job putting together an exciting program for this week's workshop. I hope you enjoy the week. And let me hand over to Adam to say a few words about the workshop.
Thanks, Peter. Thanks to the Simons Institute for letting us organize this workshop. I know the organizers and I had a lot of fun putting it together, and we're really excited for the program. Just a very brief overview. Today is primarily about testing. It's a learning and testing workshop, but today we'll be focusing more on testing and property testing problems. Tomorrow we'll have a lot of talks on learning on graphs, and also we'll feature some mini hardness results, computational hardness results. If you're into neural networks and deep learning, then Wednesday is really your day. We'll have several talks focused on that topic. On Thursday, we'll be looking at a lot of recent advances on graphical models, both from a computational and statistical perspective. And then on Friday, we'll have a variety of problems that are core to kind of computational statistics and robust learning. So the whole week will be focused on learning and testing, but from varying perspectives. And as I said, we have an all-star lineup of speakers, beginning with Maryam here.
Thank you. So let me share my slides. Okay, so thank you. Today I'm going to talk about testing monotonicity of distributions over general posets. This is a joint work with Themis Skouliakis, John People, Renee Dribenfeld, and Anna Gyatpinyani. We routinely model real-world data as random samples from some unknown distribution and perform inference tasks based on that underlying distribution. An important example of such inference tasks is to understand the properties of the underlying distribution. These properties can be pretty much anything, like whether a distribution is uniform or two random variable in our feature sets are independent from each other, support size, or the shape of the distribution. Distribution testing is basically a decision version of this problem. So let me formally define what it means to test a property. So the setting of the problem is that there is an underlying distribution Q, which we assume it's over the domain of 1 to n. Basically, n is the domain size. We receive random IID samples from the distribution Q, and we want to design an algorithm or a tester which can distinguish whether Q is in the set of a distribution that has the property, or it is in a set of epsilon far from having the property. By that, I mean, for a distribution is called to be epsilon far when for every, whenever the distance is at least epsilon to any distribution in the set pi. So the goal is to distinguish these two sets with high probability, and if a distribution is somewhere in between, either answers are accepted. The main goal in designing tester is to make sure that they have the optimal sample complexity. And this is the sample complexity we usually think of a non-asymptotic version. And let me just clarify the term. It means that we want to find the sample complexity up to constant factor. And this is in comparison with other fields that they usually think about the convergence rate, and other versions of these problems. But we make sure that to find the sample complexity up to constant factors, and other efficiency parameters like time complexity and memory can also be important after we find the right sample complexity. Several properties have been considered in the literature, and I'm sure that you're going to see many more of them in the workshop. Estimating support size, testing whether a distribution is uniform, testing whether it's equal to another distribution, shape of the distribution, and many more have been already studied. So let me define the problem of testing monotonicity and talk about our results. So I will start by defining a monotone distribution. Suppose we are given a poset, which is represented by a directed acyclic graph on n nodes. And we have a distribution Q on the nodes of this graph. We say a distribution Q is monotone if for every directed edge from U to V, we have the probability of U is smaller than the probability of V. So now the goal of testing monotonicity is as follows. We have random samples from Q, which are a set of vertices, and we are given the description of the poset G. So we have full knowledge of how the how the nodes are connected to each other, and we want to distinguish whether Q is monotone or epsilon far from monotone in L1 distance. Why this is an important problem. Monotonicity is an important structural assumption. If we know the underlying distribution is monotone, we can actually perform several tasks much more efficient when we don't have this information. For example, entropy estimation can be done exponentially faster when the underlying distribution is monotone. And also, it's the main building block of studying the shape of the distribution. So for testing K-modality, an important piece is to be able to test the monotonicity of a distribution. There are two sort of generic and naive results for the upper bound and the lower bound. The basic upper bound is that you can just learn the distribution in O of n. And when you have the distribution, it's pretty much, it's very easy to test it because you have the description of the distribution. And there is also a naive lower bound of the square root n, which comes basically from birthday paradox. You basically need at least a square root n sample to see any repeated sample. Prior to that, you basically see a bunch of unique elements. And for most reasonable set of Posets, this is impossible. It's impossible to basically test. So these are sort of this is basically the range of the sample complexity that we want to work with. Prior to our work, many Posets have been considered. I'm not going to go through the details of these results, but basically what I want to emphasize is that the sample complexity of this problem has underlying Poset. Okay. Yeah, and I forgot to say, if you have any question, feel free.
Actually, I have a question. Can you go back to the last slide? So the n in the Boolean hypercube refers to the size or the dimension of the hypercube. Like, what would be the testing complexity for the Boolean hypercube?
So it's so n is the domain size. So for the hypercube, it's actually 2 to the d, or the dimension. So it's actually linear in terms of the domains. So it's like if the hypercube is of size of dimension d, it's like 2 to the d divided by d, polylog d, poly d, sorry. Okay. So let me give you a brief summary of our results. We have a few upper bounds. The first one is an upper bound of n over log n, n over epsilon squared log n for a matching poset. And we also have an upper bound for a general poset with bounded maximum degree, which is O of d max times n over log n samples. We have a few lower bounds as well, a lower bound of n over log n for matching posets, and this is tight given the result in the previous slide in terms of n. And using this lower bound, we were able to get a lower bound for hypercube posets. So here again in the second bullet, n is the size of the hypercube. So think of it as 2 to the d. And by embedding the hard instance for the matching problem into some middle layer of the hypercube, we were able to get an almost linear lower bound for this problem. And after our paper, Rubinfeld and Vasilian shows an upper bound of n over log n for this problem as well. For the rest of this talk, I'm going to focus on the lower bound for the matching and explain our the sketch of our proof for this part. Okay, if there is any question, this might be a good time to ask it.
Could you just go back to the previous result? How should I interpret this n to the 1 minus square root epsilon for the hypercube? So if epsilon is a constant, it's like.
So basically this particular, so okay, we have two versions of this lower bound. If epsilon is a constant, then obviously we're still far away from linear result, but we have another result which says when epsilon is equal to 1 over log n to 2.5, I think, then you get the lower bound of omega of n times log n. So obviously this is not, it's because there is an interdependence between n and epsilon, this is not, we cannot really interpret it as a linear lower bound, but it basically says for any distribution that their dependence to epsilon is not exponential, you get a lower bound of n over log n, like n over poly log n. So it's but if you just so if epsilon is sufficiently small, or if it is 1 over poly log n, you can do something better, basically.
I see. Thanks.
There was another question from the audience. So is there a poset known for which the lower bound is actually known linear lower bound is there?
No, I think for a while we were thinking that the hypercube might. No, actually, even for the hypercube, we know that prior to our work, we knew that it's not the case. Okay, so I don't know, and I think the answer is no, to the best of my knowledge.
Okay, so, thanks.
And in general, if you have a property that, like for example, for matching, you can actually shuffle the labels and things pretty much remains the same. For such properties, you can't really get, like the lower bound is, the upper bound is n over log n. So for some specific structures, it may, you know that it cannot happen. Yeah, so let me continue to the sketch of our proof for the matching, for proving the lower bound for matching. To solve this problem, we introduce a new property. We call it a Tbigness. We say a distribution Q is a T-big distribution if for every element I, the probability of I according to the Q is at least T. One important thing to note about this property is that it doesn't really care about the labels of the elements. So if you shuffle the labels of the elements, it doesn't change the fact whether a distribution is T-big or not. we show a reduction from Tbigness to monotonicity, and the reduction is simple. Suppose that I want to test the Tbigness of a distribution Q. I create a distribution P as follows. The distribution P over matching as follows, and we have n edges. On the top nodes, I put the probability of Qi, and on the bottom, I put probability T, and assign, basically normalize this setting and assign P to basically be this distribution. It is not hard to show that if Q is a T-big distribution, obviously P is monotone, and if Q is epsilon far from being T-big, then P is theta of epsilon far from monotone. So now, instead of proving a lower bound for the monotonicity problem, I can prove a lower bound for the Tbigness problem, and it immediately gives me the lower bound I want. So now we focus on lower bound of n over log n for Tbigness problem. Let me give you a plan that we have for proving this lower bound. Remember that if we have a T-big distribution Q, and we draw a bunch of samples from Q, the tester, after receiving this set of samples, should output accept with very high probability. And on the other hand, if I start with a distribution Q prime, which is epsilon far from being T-big, then the tester should reject. Okay. Our plan to prove the lower bound is to come up with two randomized processes, which I will define later, for generating distributions Q and Q prime, such that their sample sets are indistinguishable if we draw too few samples. And this gives an immediate lower bound for the tester, because the tester obviously has to distinguish these two set of samples. Okay. So let me explain what it means to have indistinguishable samples. So this part might be obvious to the people have seen this before, but I thought it's important to talk about it so the people who are not haven't seen this before may also enjoy it. So it's important to understand what is the information in the sample set. What is the informative part? There are several representations for samples. We have seen lists, and obviously we can, from a list, we can actually draw a histogram, so we can keep track of the frequencies of each element. But as I mentioned, for Tbigness property, we don't really care about the labels of the elements, so we can actually make this more concise and only care about the number of elements that appeared at a certain time. So I'm totally ignoring the labels, but for example, in this list, there are three elements that they appeared only once, one element appeared twice, and one element appeared 3 times. There is another way to base, which is equivalent to this one, is to basically, save just the number of collisions in the list. And what is a collisions or k collisions? So we usually say 2 samples collide if their values are equal. So for example, the first sample and the third sample here, they're both 4, so it means that they collide with each other. We say we have a k-wise collision when we have k samples that are equal to each other. In this sample set, there is one 3-wise collision, which is the element 4 that appears 3 times. And there are 4 pairs of samples that are colliding with each other. 3 of them comes from element 4, and 1 of them comes from element 1. And we have 8 1-wise, the number of samples we have. It is known that it's very actually easy to show that if you have any of these representation, you can find the other one up to labels of the elements. But there is this last representation that collision statistic, which has a very nice property. So the expected value of the number of k-wise collision is exactly the case moments of the distribution. And so basically, it's a very inaccurate statement, but basically what you can, so any set of samples that you have, what you can infer is the norms of the distribution, and that's pretty much the information that exists there. And one thing to note is that when K is large, then it's harder to basically estimate the moment. Like obviously if you have two repetition, like if the sample repeated twice, it's much easier than compared to the case that it happens 100 times. So as K gets larger, it's harder to estimate the number of conditions. So if I want to come up with two set of samples that are indistinguishable, and one way to make them indistinguishable is to match the lower moments of the distribution. So if I have, so basically if I have too few samples, the lower moment seems identical, so it doesn't give me any information, and the higher moments are basically invisible. I don't even get to see them. So basically there is no way to distinguish the samples from Q versus the samples from Q prime. And for the purpose of this talk, we think of the lower moments as the first log n moments and of the distribution. So if I match,
I have a question. So you said histograms and fingerprints, they information wise, they're the same. They have the same information. Is that
up to the labels? Like if you don't care about the labels of the element, yes. So
okay.
I can't really, like, yeah. So up to the labels.
Okay, and then you're saying if I have the histogram again, like with the labels anonymized and so on, then I can of course extract the KY escalation statistic, but I can also go in the other direction. That is from the KY escalation statistic, I can also obtain the histogram.
Yeah. Yeah.
Okay. And this is the part where you're saying that lower order moments are the only ones which will matter in this going back.
So basically, so if you have KY exclusion, you can actually reconstruct fingerprints, and it's basically equivalent to the histogram up to labels, yes. And that's why, like, obviously there are other ways of coming up with distributions that are indistinguishable, but one way to think about it is that this is all the information that exists in the sample set, and if I make them equal, at least for the lower moments, then they seem identical in some sense. Okay.
Thanks.
So going back to the to our scheme for the lower bound, I want to come up with two randomized processes for Q to generate Q and Q prime, and I have a few demands here. Basically, I want to make sure that the Qs are T-big, Q primes are epsilon far from T-big, and all of these statements should hold with high probability. And I want to make sure that in expectation, the moments of Q and Q prime are, the lower moments of Q and Q primes are identical. So let me focus on this randomized processes and define them, how we actually generate Q and Q prime. Suppose we have a distribution P, or think of it as, we call it prior, and think of it as the parameter which we will define later. So this is basically a set of parameter. And from the prior distribution P, I want to generate a distribution Q over n elements. The way that we generate this distribution is that by we generate n random variable from P, and the expected value of these random variables are 1. And we define the distribution Q to be the vector of these random variables Vi's divided by n. And in expectation, some of Qi's should take the value of each of those random variables for 1. And in general, this may not be a distribution. There are some subtleties that we need to take care of, but for now, just assume that Q is actually a distribution. Basically, my goal is to find two distribution P and P prime, such that, as I mentioned, one of them generates T-big distribution, the other one generates epsilon far from T-big distribution, and their sample sets are indistinguishable. So if I find such P and P prime, my lower bound is immediate. Like it's just based on whatever I explained prior to this point. To find P and P prime, what we do is to basically formulate an LP. I don't want to go through the details of this LP, but basically I formulate all the demands that I had. I made sure that the expected value of VIs are 1, and the second line, the third line is basically tells that the moments of the distributions that are generated match in expectation, and the last line basically ensures that the random variables from distribution P, they're all of them are certain, all of them are above a certain threshold, which means that they will generate T-big distribution, and the other distribution P prime generates samples VI primes such that a bunch of them are actually 0. And in the objective, we want to make sure at least an epsilon fraction of these elements are assigned basically got the probability 0, which made the distribution far from being T-big. Okay, so this is the LP. So in a couple of the steps, we basically show that this LP is equivalent to another LP introduced by Wu and Yang. And roughly speaking, if you take the dual of that LP, it will turn into a problem of estimating a function with polynomials, with low-degree polynomials, and the low-degree polynomials comes from the basically the first log n moments that we wanted to match. And the solution of that LP comes from Chebyshev polynomials. And given that their LP has a solution, implies that our LP has a solution. So I have to set of parameters P and P prime, which gives me the lower bound that I want. So basically this is the end of the proof. If the P and P prime exist, I know that the lower bound exists. So let me summarize what we talked about. So I give a general overview of definitions of distribution testing. Then we focus on giving a lower bound for a lower bound of n over log n samples for Tbigness property, which immediately gives a lower bound for monotonicity of testing monotonicity of matchings, and it gives us a lower bound for the monotonicity of testing monotonicity of the hypercubes. And that's it. Thank you.
Thank you, Maryam. We actually have plenty of time for questions. So we had a few questions, but okay. Yeah, I mean, if there any, so one question we have is there an order n over log n upper bound for the matchings?
Yes. Yeah.
Okay.
It was in one of our program, but it's not. Basically, the idea is at a high level, the idea is to learn those fingerprints that I was talking about. And if you learn that, you can learn the match.
So this is, so actually I had another question. I did not quite understand the reduction between Tbigness and because why are we able to simulate it? I was not entirely clear about the reduction, if you can.
Okay. Oops. I think it was slower. Okay. So the input is the input is samples from distribution Q.
Right.
But I want to generate a sample from distribution P. So basically, with a probability proportional to NT and 1, I can pick whether to generate the sample from top or generate the sample from bottom. And if it's from bottom, just output a uniform sample. And if it's from top, you look at Q and ask for a sample. Okay. And this is how you generate sample from P. And if Q is a T-big property, then this should be monotone, because after normalization still remain monotone for each A will have that property. And if it is far from monotone up to that normalization, you are still far from being monotone.
Okay.
Sorry, if it's far from being T big, it will be.
Are there other questions? I'm trying to keep track of the Q&A thing. Actually, I have another question in the meantime. So for Posets, I don't know, but there must be some combinatorial quantities, right? Something like a width of the Poset or something like that. And is there any, is there a property, do you suspect, or is there something known, property testing, lower, upper bound for testing monotonicity over Posets, which is naturally related to some combinatorial quantity characterizing the poset, like the width or something like that? Or height, I don't know, like, whatever, length of the longest chain, number of anti-chains, whatever, something like that.
So, okay, so yeah, so these are the ideas that actually, so for, I think the previous upper bound, or, so I think that, I don't quite remember, but there was another, I think there is a lower bound for general Poset, and it's a paper by one of the Valiants with other people. Sorry, I don't remember the exact set of authors, but basically what they do is exactly what you said, like they embed matchings in a Poset, and the longer, and so basically you need many matchings, many chains, and the hope is that to have longer chains. So they have been used in different Posets, like the transitive closure. Like, for example, we had upper bound which worked with the maximum degree of the transitive closure. So that's also something that might be interesting. But I don't know if there is one specific, at least I think it's not known yet, that there is a specific combinatorial characterization of the Poset which directly give you a lower bound and an upper bound.
Are there any other questions? Okay. Well, if not, then let's thank Maryam. And the next talk is by Eric. I'm not, should I stop, Jesse, should I stop the recording?
Yeah, I don't think we need to stop the recording, but we could just start at 11:30, maybe take a little break.
Okay, yeah, okay, great. And we are not doing Berkeley time, right? We are like doing actual time, right?
Not sure what you mean by that.
Oh, I meant, are we starting 5 minutes after the, are we starting 5 minutes after the scheduled time?
No, let's keep on the schedule.
Okay, that's what I meant. Okay. Anyway, let's take a break and let's start at 10. Sorry, what time are we at? 9:30 Berkeley Pacific time. Yeah.